Welcome to the GEOTOP-A seminar. Today we have Chris Soteros from the University of Saskatchewan. We'll be talking about establishing that knots and links are localized for ring polymers and nanochannels. Chris, take it away.
Thank you, DeWitt, and thank you very much for you inviting me and also to the whole scientific committee for this seminar series. And also especially thank you for Carlo for all the organization. I'm really honored to be have the opportunity to speak in this seminar series. And maybe just a little about where I am. I'm at the University of Saskatchewan, as DeWitt said, that's in Saskatoon. And here are coordinates. And currently, I think it's -2 Celsius outside. And I acknowledge that I live and work on Treaty 6 territory and the homeland of the Métis. And I pay my respects to the First Nations and Métis ancestors of this place and reaffirm our relationship with one another. Okay, so I've been studying lattice models of polymers since I was a postdoc with Stu Whittington back in the late 1980s. And usually there's been dual motivations for studying these models. So partly to answer questions that arise from experiments, but also to look at mathematical questions about the models. And I got introduced to DNA topology back in the early 90s from DeWitt, who was working with Stu. And so my talk today is motivated by some DNA topology questions from DNA experiments, but also answering fundamental entanglement complexity questions about polymers and random polygons. And so in particular, today I want to highlight a proof that we've obtained related to a 1996 conjecture that's to do with knot localization. And so I'm going to be looking at the case of polygons or polymers, ring polymers in a tube. So basically, you have the scenario that you have, you're looking at, say, embeddings of polygons with a fixed link type, and in a tube where two of the dimensions are restricted, but the polygons are allowed to grow in one of the dimensions. And we usually look at each polygon of the same size, say, as being equally likely. And so sort of just thinking about it, if you have, say, a fixed knot type, so suppose the knot type was 3-1 composed with 3-1, trefoil composed with trefoil, then for entropic reasons, you might expect that on average, the where the knot is might be small compared to what the rest of the size of the rest of the polygon. And so it sort of behaves like, so there's sort of two different regions here where you've got what they call the knotted part. And then because you're in the tube, you're essentially only growing in one direction, one dimension. It's typically thought that mathematical arguments in the tube are fairly straightforward. And so, so people believe that knots are localized. And similarly, if I have a link type, fixed link type with, say, this is a hop link composed with another hop link, that again, in that scenario, the linked portions will be small. But what I want to, so it might seem obvious to some that this is what you would expect. And maybe because it's in the tube, you might think that it would be easy to prove. But what I want to show you today is that actually it's not so easy to prove. And but we do have a proof for the smallest tube that admits non-trivial links and knots. And the proof is in this paper that's on the archive. And then if I have time, I'll talk about another model where we just suppose we have two polygons, so two components, and we insist that both polygons have the same span and sort of extend across the tube equally. And there because sort of linking, so for this model, it's interesting partly because you can show that linking is inevitable, so that all but exponentially few of these things are linked. But the linking is perhaps not localized anymore because, of course, you can have one piece crossing the other, one polygon crossing the other, but that can be undone later on. And so sort of identifying where the actual link part is might not be easy. But on the other hand, if you have a knot in your connect sum, then that could still be localized. And so I'm going to talk about, if I have time, some results that we have related to that. Okay, so that was an overview of what I want to talk about. So just to sort of put things into context. So when I talk about saying that I'm modeling DNA, well, I'm really thinking this is the DNA double helix, but I'm looking at it macroscopically. So basically, we're representing the double helix by the center line, and then we're putting it on a lattice to even simplify it further. Of course, on the lattice, I'm going to be looking at simple cubic lattice. You've only got right angles and 180-degree angles. So that seems very restrictive. But actually, if you have a long enough walk or a polygon, the fact that you're on the lattice can be lost if you look at it. There's still a lot of conformational freedom. And in the lattice models I'm going to talk about, we usually look at, so I'm either going to be talking about, mostly I'm going to be talking about self-avoiding polygons or sets of self-avoiding polygons. So this is an example of a self-avoiding polygon on the simple cubic lattice. Basically, it's a simple closed curve on the lattice, and it's not allowed to intersect itself. And I'm going to be looking at equilibrium models in the sense that we will we'll count these things or study these things by their size. One measure of size would be the number of edges in the polygon, and consider that each polygon of the same size is equally likely. And so then looking at something like the probability of knotting would be a counting problem. You would count the total number of polygons of that size and look at the number of them that say were the unknot, and that would give you the probability of the unknot. One minus that would give you the probability of knotting. And so, okay, that makes it sound like it should be easy, but the thing is, counting these walks and polygons on the lattice is a challenging problem in itself. They're only known exactly up to small numbers. So on the simple cubic lattice, so this is the simple cubic lattice over here, the largest it's known exactly to is to 30, for walks is 36 steps. And then for polygons, it's 32 steps. And you need 24 edges on the simple cubic lattice to create a trefoil. And so, and there's not many trefoils of length 24 relative to the total number of polygons. And I think you can get a figure 8 at length 32, or you might, I've forgotten now. You might need 34 edges for a figure 8. So just looking at what you can do exactly is not going to get you very far in terms of figuring out properties of the knot probabilities, for example. However, you can use combinatorial arguments, and so in particular, one of the first results that was proved for using a lattice model was the Frisch-Wasserman-Delbruck conjecture. That was a conjecture in the 1960s that you would expect that sufficiently long polymers would be knotted with high probability. And DeWitt and Stu Whittington proved that using a lattice model, and independently Pippinger And they showed that all but exponentially few self-avoiding polygons on the simple cubic lattice are knotted. And I will outline what the ingredients of that argument is. And so before I said my motivation is to look at, or my goal is to look at these tube results that we have. But the original conjecture about knot localization is actually for unconfined polygons. And that was also the Frisch-Wasserman-Delbert conjecture was proved for unconfined polygons. So I just want to review a bit that argument. So we let Pn be the number of distinct up to translation n-edge self-avoiding polygons in the simple cubic lattice, and Pn01 be the number of those that are unknot. And then we can also define Pnk to be the number of those that have knot type K. So what Sumners and Whittington proved was that the probability of knotting, which is 1 minus the number of unknots divided by the total number, goes to 1 exponentially like this. And I'll say on the next page, they proved it using a pattern theorem, and I'll talk about the ingredients of that on the next page. Myself and DeWitt and Stu extended those arguments in the early 90s to showing that the probability of knot type K, so that's Pn of K over Pn, has to go to 0. Other than that, we don't have a lot of detail. We don't have a lot of results for Pn of K. And numerical work by Orlandini et al., there was a paper earlier in 1996, and then in 1998, they conjectured that the scaling form for these counts goes like n to the fk times the number of unknots, where fk is the number of prime knots and k is knot decomposition. And so this is consistent with the idea of knot localization in the following sense. So if you had, so looking at this picture here, it's consistent with the idea that you basically, if you have a trefoil, on average, it's like you have an unknot, which is decorated by a little trefoil piece. And why is this consistent with it? Well, if you were going to then count the number of trefoils, then it would, if they were mostly small, then you could say, then this would say you could get the count by taking a typical unknot and then choosing of length n, choosing any of the n positions along the unknot and inserting a little trefoil pattern. And so that would give the n to the 1 in front of the Pn01 in that case. And suppose you had multiple knots in your prime knot decomposition, then start with an unknot, pick fk places to put your little pieces of the knot, and so n choose fk places, and that would give you a factor of n to the fk. Okay, but none of that has been proved. So what has been proved in general? So you can use concatenation arguments. So the idea that if I take one polygon and another polygon, one of n steps, the other of m steps, then I can bring sort of the top edge of this one close to a bottom edge of this one, and then join the two polygons together in a connected sum type of operation and get a new polygon also on the lattice. So this gives a relationship like this for the counts. And because you know the number of polygons is bounded above by, say, the number of random walks on the lattice, then these two pieces together tell you this limit that defines the exponential growth rate for the number of polygons exists. So you can show they do grow exponentially. And then because this concatenation operation is a connected sum, you can do the same thing for counts of unknots. So you can show their exponential growth rate exists. And then, as I said on the previous page, what DeWitt and Stu proved is that they used a pattern theorem for self-avoiding walks that had been proved by Keston, and they adapted it to work for self-avoiding polygons. And they show that all except exponentially few self-avoiding polygons contain a tight trefoil pattern. And so, and it's, we call it a tight trefoil pattern because if it occurs anywhere in a polygon on the lattice, it means that that trefoil has to be in the knot decomposition of the resulting polygon knot type. And so because of this pattern theorem, since all but exponentially few polygons have to contain this pattern, it means that the unknot polygons are exponentially rare in comparison to all polygons. And so their exponential growth rate is strictly less than that for all polygons. And that's what gives the probability of knotting goes to 1 exponentially fast. So, but that's really the limit of what can be proved theoretically in terms of probability of knotting. You can show that you can concatenate an unknot to any polygon with another knot type and get a new polygon with the same knot type, K, but that just gives you a lower bound. In order to, so we don't even know that this exponential growth rate for polygons of fixed knot type exists. We need to get, so it's believed that their exponential growth rate is the same as for unknots, but we need to get an upper bound where we take a polygon with a fixed knot type and turn it into an unknot in order to show that was true. So, oh, I don't seem to have it on this page. Oh yeah, I had it on the previous page. But what's believed is true, just to reiterate, is that, so this is saying the exponential growth rate will be the same for fixed knot type polygons as unknots. And that the difference is only in the asymptotically in the next term, the n to a power term, and the power goes like the number of knots in the knot decomposition. So what about if you have multi-component systems? So here now you have to be careful, first of all, when you define the counts. So suppose I had, I want to count systems of 2 polygons. Well, if I just count up to translation, and if the 2 polygons are split, then there's going to be infinite number of those, right? So because they can be far apart. So you normally have to then, for the counting to make sense, you have to put some restriction on how far apart the 2 polygons can be. So for example, you can find them to a box with side length equal to the length of the polygon. All right, so you can do that, and then you can talk about the number of systems of polygons, say with C self-avoiding polygons making up the system, and n edges in total, for example. And then you can talk about the number with a fixed link type, and then you can talk about the special case where they're non-split, so they're linked. And you can ask then what's the probability of being linked? Well, in the typical type of scenario where you can define these things, you can actually, the probability of not being linked is so the number that are not linked compared to the total number is, it does not go to 0 exponentially, and basically it goes to a constant, or well, no, sorry, it could go to be 0, but not exponentially fast. So they both these things have the same exponential growth rate. So in some sense, you don't know that linking is inevitable. Being linked is inevitable. But some recent numerical results by Orlandini et al., if you restrict yourself to fixed link type, fixed non-split link type, their numerical results in that case are consistent with the number of embeddings of that link type grows asymptotically like the number of unknots, and then n to the FL, where FL is the number of prime factors in the link decomposition of L. And so again, it's the similar kind of argument that basically you've got an unknot, and then the little, either you could have a trefoil added, or you could have a little piece added to make your link that's in your prime factorization. So this is also believed for non-split links. Okay, but again, not a lot can be proved. All right, so what I'm going to talk about is the situation where you're confined to a tube, and there is experimental reasons for considering, for example, DNA and nanochannels, so tube-like environments related to recent experiments, single molecule experiments involving DNA and nanochannels. And now the experiments are non-equilibrium typically. Typically, the DNA is driven through a nanopore by electric charge or some other forcing mechanism. And we're looking at equilibrium models, but the non-equilibrium experiments do point to open questions about what are the characteristics of knot and links under this kind of confinement. And so, for example, what is the typical size? And then that opens questions to, well, how do you measure the knot size or link size? And that's certainly an interesting question. And then I will say that if once you have a measure of the knot size, then we say the knot is localized in a length-end polymer if the ratio of the knot size to the polymer size goes to 0 as n goes to infinity. So you really have to have a situation where you're looking at the length of the polymer go to infinity, and you have to have a measure for this knot size to even talk about localization. And then we say it's strongly localized if the ratio goes to, if m goes to a constant as n goes to infinity. And then there's some interesting questions related to whether different modes of knotting or linking are more probable. All right. And so we've been using lattice tube models to look at these kind of questions. So this is, we're looking at sublattices of the simple cubic lattice, where we restrict 2 of the dimensions. So the y direction and the z direction are limited to go between 0 and L and 0 and M, say, in an L by M tube. And we let the polygons grow in the x direction. In this case, we can use 2 measures of size. One is either the number of edges in the polygon, or we often also look at the span of the polygon. So that's the span in the x direction, the distance from the leftmost plane to the rightmost plane that the polygon exists in. And depending on which size we choose, we'll assume that each polygon of the same size is equally likely. So often either it's same number of edges or same span. And but people have been looking at polygons and walks in tubes as models of polymers under confinement for quite a while. It goes back to at least the 70s. And then Klein in 80, and then Elm and Jansen expanded on the mathematics behind it, used transfer matrix methods to study these lattice models. And back in '89, Stu and I proved a pattern theorem for self-avoiding walks in tubes. And then in '98, I obtained a pattern theorem for polygons. And from that, could show that the FWD conjecture works for polygons in tubes. The reason the pattern theorem for walks doesn't help in this case, I had to get a separate pattern theorem for polygons, was because polygons, unlike in the whole lattice, polygons and walks have the same exponential growth rate. In the tube, polygons have a smaller exponential growth rate than walks. Okay, and so the whole idea of the transfer matrix method is that essentially a polygon in a tube is only growing in one direction. And so it's like a one-dimensional word where you can look at sort of all the configurations, sort of ignore the beginning, for example, but in the middle of the polygon, you can think of this polygon as being made up of these different configurations on a unit length slice. And there's only so many, given a particular size of the tube, so height and width in the y direction, there's only so many configurations that can occur on a single slice. And then only certain configurations can follow other configurations. And so basically a polygon in the tube is just a word made up of these letters of the configurations that can occur on slices. And the transfer matrix is used to store information about which letters can follow which other letters and still guarantee that you get a polygon. And so this is the transfer matrix for, in the case of a 2x0 tube, so they're planar. So there's these planar configurations that can occur on the slice. So you have a row for each configuration and a column for each configuration in the matrix. And if this one can follow that one, you put a non-zero entry, and with some kind of indeterminate raised to a power where the power is used to keep track of, say, if you're counting the number of edges, or keep track of things that you want to count. And then the partition function, or that's in statistical mechanics terms, or the generating function for these counts, this is the number of polygons with n edges and span s, can be obtained from the transfer matrix. And then because you can write this as the sum, so G is the transfer matrix here, B is the start matrix for the options at the beginning of the polygon, C is the end matrix for the options at the end of the polygon. And because this is proportional to 1 over this determinant, it means that the radius of convergence of this power series is related to the eigenvalues of the transfer matrix. And also you can get asymptotic properties of these counts from the eigenvalues of the transfer matrix. And so actually the mathematical theory for the total counts is you can get a lot from the transfer matrix. So in particular, you can get that the number of polygons, say, with n edges grows exponentially with some mu. And if you actually have the transfer matrix, you can calculate mu exactly. And then there is no n to a power term. The next term is a constant. And that constant can also be determined from the transfer matrix. And then you can get a pattern theorem from the transfer matrix because basically one way to look at it is the transfer matrix allows all the possibilities to go from one letter to another. But now if you're looking at removing a pattern, you can show that that's equivalent to, say, removing a row and a column of a suitable transfer matrix. And so then that will affect the eigenvalues, and then you can show the eigenvalues will be strictly different, and then that will mean the exponential growth rate will be strictly different. And so that's the way you go about proving a pattern theorem. Okay, so all right, so actually, if you're looking at all polygons in the tube, the mathematical machinery is very powerful. And so really you would say, okay, well, looking at polygons in a tube is easy then, right? And in fact, okay, but when I'm looking at all polygons, I'm allowing all possible knot types. And so basically anything that can occur in a polygon will occur a density of times. So will occur epsilon p times n times in a long polygon, and also you're going to have lots of places where you just have two edges, so we call that a two section, and so you're going to be able to break up this polygon into connected sums, and so in some sense then the average distance between two sections will go to a constant. And so in that sense, I guess anything that happens will be localized. But that's assuming that you have an arbitrary knot type. Like you have no control over the knot type. But the original question I asked is, and those conjectures were supposing the knot type is fixed. Well, then we still have, then that's still a problem. So suppose I fix the knot type to be the unknot. There's no pattern, there's no transfer matrix for unknot polygons. Whether something is unknotted or not is not a local property, it's a global property. So I can add things, add patterns, but until I know what the whole thing is, I don't necessarily know whether I have an unknot or not. And so there's no transfer matrix. We can prove that the exponential growth rate for unknots exists by concatenation argument, the same way we did without confinement. But, and we conjecture that you have the same form for any tube size that was conjectured for without confinement. So that is the number of size n with fixed link type goes like the number of unknots times n choose the number of prime factors in the knot decomposition, or like this, that gives you the F to the L term. And so we expect if you fix the knot type, they grow exponentially, the same as unknots. But none of that has been proved, except for we have been able to prove it for the special case of the 1x2 tube. So that's the smallest tube that emits non-trivial knots and links. And so we believe it holds for other tube sizes, and we have numerical evidence based on Monte Carlo simulations that it does hold for other tube sizes. And but so basically this proof that we have for the 1x2 tube is the first proof of any kind of this conjecture. So I just want to talk to you about what are the ingredients of the proof to show you that it's, even though we're in the tube, even to do it for the smallest case is non-trivial. So the idea is that in order to prove this, we want to say, if we start with an embedding, we want to relate embeddings of, say, any fixed knot type or any fixed non-split link type. We want to relate the number of these things to the number of unknots. So basically we need a lower bound and an upper bound. So for a lower bound, we want to start with an unknot and somehow turn it into the link type that we're interested in. But we want to do it in such a way that we're going to get this n choose FL factor. All right, and then for the upper bound, we want to start with an embedding of one of these with fixed length type, and somehow we want to cut out the linked parts and turn it into an unknot. And we want to do it in such a way that we're not cutting out too much, so that in worst case scenario, we have an n choose FL type factor. So for the upper bound, that involved getting some new knot theory results, primarily due to my collaborators, Kai Ishihara and Koya Shimakawa, who are in Japan. So it was too early in the morning or late at night, depending on how you look at it, for them to attend. So I'll just sort of summarize the idea. So in the 2x1 tube, you can have knots or links, but they all have to be two bridge or four plats or connected sums of those. And so the arguments rely on that fact. So that does simplify the possibilities. And so for every polygon in the tube, for example, or a set of polygons, you can get, if you just have a prime polygon, then you can get a four plat diagram, and then, you can get a projection that can be turned into a four plat diagram. And then what Kai and Koya proved is that you can use a minimal diagram of this four plat to identify a three braid word and a location where to insert the three braid word, which can, that same word or a modification of it, where, so one is the reverse word, another is the flip word, can be used in any diagram of the link to identify a position and then insert this word and turn the diagram into the diagram of an unknot. And then because of the way the restrictions in the 2x1 tube, you can show that any prime factors in the polygon are isolated from each other. And so you can get separate projection diagrams from each piece, and then you can turn the word that you get from the theorem into a lattice configuration, and you can identify where to insert this into the lattice and to turn your original fixed knot or link type polygon into one of the unknot. And the important thing is that the length of this thing that you insert is limited by the minimal number of crossings in the link type. So it doesn't depend on the size of the polygon at all. It only depends on the crossing number of the link type. And so because of that, we're able to get an upper bound of the form that we need, because we're not changing too much and in only FL places. Okay, so I'm starting to run out of time. So in terms of the lower bound, so the upper bound required new knot theory involving braids. And so one of the main difficulties or challenges or with the novelty was that to show that you can, whatever you do in the minimal diagram, you can also do on any diagram. And it involved showing that these operations on braid diagrams preserve the link type. Okay, so that's for the upper bound. For the lower bound, the idea was that if we start with an unknot, if we could show there's a lot of places where we have a two section, so then if we have a a pattern that when we insert it will guarantee the link type or knot type that we want, or a prime factor of the knot or link that we want, then if it's what we call a connected sum type pattern, then we can insert it at any of these two sections and turn our unknot polygon into one that has the knot type that we want. But in order to get the bound of the kind that we want to be able to do that in order n places. And so that means we need to know that there are order n, if n is the size of the polygon, of places that have just two edges, these two sections. And so for that, we needed a pattern theorem for unknot polygons. So we have a pattern theorem for all polygons, but that's not going to help us. We need a pattern theorem for unknot polygons. So we need to show that all but exponentially few unknot polygons have a density of these slices with only two edges. And so the way that we did this for the 1x2 tube was we took advantage of the fact that we actually had the transfer matrix for all polygons for the 1x2 tube. And then we removed all the patterns that correspond to two sections from the transfer matrix for all polygons. And so then that gave us a count. That gave us the value for one of these. I forget which one. I think this one is. Okay, I think this one is, all right. We got our transfer matrix and we got an upper bound on the exponential growth rate for all polygons which don't contain any of these two sections. And then of course, the unknots that don't contain any of the two sections, their exponential growth rate can be at most that. And then we got a lower bound on the exponential growth rate of unknots by actually counting unknot polygons and using those counts to get a valid lower bound. And so then putting these together, it's showing the exponential growth rate for unknots that don't contain any of these two sections must be strictly less than the exponential growth rate of all unknot polygons. And then we can do additional combinatorial arguments to show that all but exponentially few unknots have a density of these two sections. And so then we can insert any knot pattern or link pattern that we want at these two sections, and we get the upper bound of the kind that we wanted, that we need. And so that proves the conjecture for the 2x1 tube. But we can also say a bit more. We can actually, once we have that proof of the exponential growth rate of unknots and fixed knot type knots or links, non-split links is the same, we can use that to get also a pattern theorem for any fixed non-split link type in the tube and show that they have a density of two sections. And so if my link type was the trefoil 3-1, 3 composed with 3-1 composed with 3 run, well, those this isn't the only way that could happen, but suppose those three patterns occur, then the rest of the thing must look like unknot pieces, and then there'll be lots of two sections in that. And so basically since there's lots of two sections, it means these the distance between the two sections is going to go to a constant. And so that's an indication that wherever the prime factors are, they're going to be limited in size. The distance where the prime factors are is going to be going to a constant as well. You can also show that if you have the knotted part growing with the length of the polygon, that those are exponentially rare. and that the ones, if you fix the link size or knot size to be a constant, at most a constant, then you can show their scaling form is the same as all unknot polygons, or all fixed link type polygons. Okay, so that's an overview of the proof of that argument. And so I hope I convinced you that it's non-trivial to prove. And okay, so let me add, why can't we do it in more than 2x1 tube? Why can't we go up to 3x1, for example? Well, we probably can do the lower bound for, we probably get a pattern theorem for unknot polygons for higher tube sizes, because we do have the transfer matrix for some slightly larger tube sizes, but the current argument does rely on having the transfer matrix. So we, at the moment, the highest tube size that we actually have the transfer matrix for is 3x2, because the number of patterns that can occur on a slice grows exponentially, right? So the transfer matrix itself gets very large as you increase the tube size. So we can probably do the lower bound argument for higher tube sizes, but the problem for the going to a higher tube size, even 3x1 for the upper bound, is that, okay, even if we, so first of all, you can have more than just two bridge knots or connect sums of two bridge knots in 3x1. But even if we restrict it to those, the problem is there's just that much more freedom in the tube that we can't be sure that the prime factors are isolated from each other in the tube. And so we can't easily get the 4-plat diagrams for the different prime factors. That's one of the issues. So it's not so easy to prove these things in the tube, but we did. And so I guess I have 2 minutes. I'm not sure. Okay, so I did say if I had time, I would try to say something about this special case model where we just look at 2 polygons and we force them to have the same span. So we call these 2 SAPs. And here's a picture of 2 examples of 2 SAPs. This one is, bottom one's in the 1x4 tube with span 50, and this is in a 2x1 tube with span 3. So this one's a hop link. I forget. This one might be a hop link too, I'm not sure. So we use QTS to count the number of pairs. We typically count these by span because the span is easy to count, easy to fix. And okay, why might they be interesting? Well, perhaps could be related to replication. So when you immediately look at the replicated version, say, of DNA, at that point, the 2 DNA are overlapping. But also you can think of it as that we're focusing in on the overlap region, the region where 2 polygons overlap. And back in 2010, we proved with Klaus Ernst for the 3x1 tube and larger, there is a pattern that, and it looks like this, that guarantees that the 2 polygons will be non-split, that all but exponentially few are linked. Now that this pattern doesn't fit in the 2x1 tube, so it left open the question whether the link was exponentially rare in the 2x1 tube. And so we are able to prove that for the special case of the 2x1 tube using some of the results that we had, because they're again going to be 2 bridge, but also using the fact in the 2x1 tube, in higher tubes, if you try to concatenate 2 SAPs to create a new 2 SAPs, we're now not doing a connected sum operation anymore. And so you can take 2 trivial things and end up with something non-trivial. But in the 2x1 tube, all the trivial things are what we call untangled, and you can concatenate them and still end up with something non-trivial. And so that, combined with the fact that we can get a pattern theorem for unlinked two saps in the 2x1 tube, basically we can show that there's a density of patterns like this. And because of that, we can show that these must be exponentially rare amongst all of the two saps. We can use similar arguments and a Casson invariant to show that the unlinks are also exponentially rare amongst linking number 0 two saps. And we can show that in the 2x1 tube, the exponential growth rate for fixed link type is the same as for the unlink. But there's no knots. You can't have a knot in your prime factor in a two sap in the 2x1 tube. And so in the 3x1 tube, we don't have a nice result about like the way we do for knots and links, where the exponent goes up by 1 for each prime factor. But we do have some arguments. We have numerical results that suggest that happens, and we also do have this one here. We do have some arguments that lead us to believe it could be true, but we can't prove it exactly. We can prove something, but not what exactly would give the right results. Okay, so I've gone through that quite quickly. Just to summarize, it is possible to prove asymptotic properties of knots and link statistics for polygons and tubes. And the 2x1 results that I talked about are the first proof of a long-standing conjecture believed to hold for any tube size and for unconfined polygons. Now, the examples I looked at were where we considered each polygon or each system of polygons equally likely if they had the same size. But if we really want to compare to DNA experiments, there's other interactions that might be happening in there that might be relevant. And so how can we take that into account? And we're looking recently with Margarita, who I think is here, Marielle Vasquez, and Natasha Yanoska, looking at models of DNA RNA hybrids, such as R loops. And related to that, I wanted to tell you that we have a BERS workshop starting on Sunday, and there's room for virtual attendance, participation. And if you're interested, information about the schedule and everything is here. And if you want to email me, I'd be happy to invite you to join virtually. Okay, I think I'll stop it there. Thanks.
Oh, Chris, thank you for a great talk. And now the floor is open for questions.
Too many details or not enough details?
Yeah, well, you said you had some results for like 3x1 tubes. How about 2x2 tubes? Saying,
okay, so no, I mean, we have the transfer matrix for 2x2 two saps and 2x2 polygons. Because we have the transfer matrix, it means that we can get some exact counts for all polygons or all two saps up to a certain size, but it means we can also do Monte Carlo sampling, like independent Monte Carlo sampling from the equilibrium distribution using the transfer matrix. But that's for all two saps or all self-avoiding polygons. And so then to look at questions about knots and links, we're getting estimates, statistical estimates based on looking at the proportion that are a given knot type. So yeah, we other than proving that the knotting is inevitable, or in two saps linking is inevitable for any tube size, and that the exponential growth rate for the unknot exists, say, there's not really much more you can prove about fixed knot type things outside, beyond the 2x1 tube. So that's, you know, I think people look at the tube, it should be easy, but even for the simplest case, it's not easy. I guess that's my message. I don't know, does that answer your question, DeWitt?
More or less, but there's a lot I don't understand. So did you also say that in the small tube, the 1x2, that composite knots are sort of obviously composite because you get these two sections that separate them out?
Yeah, so basically, because there's not much room, that I don't know whether I can show it. Because so this is I think is a trefoil. So you need basically you need to, in order to put the crossings in for the trefoil, you pretty much are taking up all the available space in the tube. And so there's no room for, having another trefoil come in above.
Yeah.
So it's sort of guaranteeing the prime factors are separated. Yeah, so that is another thing that's very nice. But as soon as you go to 3x1, you can't guarantee that anymore. So that's another problem. So even if you restricted to the two bridge or connected sums of two bridge in 3x1, you still might not know where to insert the thing. So you might be able to find the thing that you should insert, but you might have to delete too much if the things are overlapping. I mean, I don't know. It may be possible, but it's not a simple, wasn't an obvious thing to extend to. We did think about it. I know Kai and Koya thought about it, and it's just a combination of tube size, freedom. Yeah, exactly. Yeah.
You also, one of the things you mentioned, that you're looking at reconnection. This is something that's very important in fluid dynamics. So I'd be really interested on anything you can say about statistics of reconnected things.
Yeah, so we did start to look at that. And I don't know what that was, that at the end. I don't know. I don't know. Anyway. Yes, we have started to look at that especially for the yes. Well, so one thing is we've classified the different types of so if I go back to the beginning, or go back here. Okay, so for example, for the trefoil in the tube, one nice thing is we can define patterns. We call them knot patterns, because if it starts and ends with just two edges, then we call it a connected sum pattern. So basically, as soon as that pattern occurs, it will guarantee whatever the knot or link type of that pattern is will be in the prime decomposition, right? Because we're basically putting it in as a connected sum. And so we can classify in the tube these connected sum patterns nicely. And then if we have a long polygon in the tube, we can cut it up. We know there's going to be a density of these places where there's two sections. And so we can actually simplify the knot identification by cutting up the polygon at every two section. And we only have to look at those smaller pieces to figure out the knot type. And then within, and then we can classify the different kind of connect sum patterns into different types. So this one is called, Nicoletti and his student, they also, I noticed that there is these two types of knot patterns in nanochannels. So this one they call the two filament one, where basically you need both strands of the polygon to know that you've got the knot there. Like basically, I don't really know I've got the knot until I go all the way around here. Whereas this one, I know I've got the knot. Okay, so why am I talking about this? The one way that we're characterizing these two filament ones is we look at reconnecting them. So we compare connecting them like this to connecting them the other way. And so this one, either way that you connect it, you're going to get the trefoil as being part of it. Whereas this other one, if we connect the other way, we no longer have the trefoil in part of what we got. So anyway, when you said reconnection, that reminded me that we were using that to sort of classify these different types of knot patterns that we saw. And also you have different type of link patterns as well. Okay, so maybe we've gone beyond the time.
There's I'm sort of hogging the questions here. It's time for somebody else to ask the question.
Well,
Okay,
I might have a simple question. Is it so? What kind of well, you said that for the 2x1 tube knots, do you have like the only kind of knots that you have are 4 plats? Is that what you said, right?
Or connected sums
connected sums.
of 4 plats. Yeah.
So is that the only thing that you can get? And so there is so you can connect the sum of 4 plats. So every connected sum of 4 plats, I can find a way to put it in the grid, or is it?
Okay, so I'm not sure it goes the other way. I think that I want to say yes, but then I'm trying to remember whether there might be some strange.
Oh,
There
constraints.
might be some strange case.
What is that?
Yeah, I can't remember, but
Okay.
definite. But I think probably anyone you come up with.
Okay. Okay. So have you addressed this kind of questions, like classifying all the possible knots that you can get from?
Yeah. So yeah. So that's right. So Koya and Kai have determined. So based on the something called the trunk of the knot or link, you can determine what tube size it will fit in.
Oh, okay.
So and then for two SAPs, working with, so I should have said the work on the theory for two SAPs was with my former postdoc, Pudapong Pongchinapaisan. And so these two SAPs, both of the polygons have to have equal length. And so he's got some results. I don't know whether I've listed it here somewhere.
There is his name.
He's got some results about what we call equal height trunk. So sort of related to the trunk, but equal height trunk, and you can use that to determine which are embeddable in as two SAPs. Yeah, so that definitely has been studied and determined. Yes, not by me, but by others. Yeah.
Okay, thank you very much for your question.
Yeah.
For your answer. Thank you very much.
okay. Well, if there are no other questions, let's thank Chris for a great talk.
Thank you all.